So I would like to start with thanking the organizers for this very nice workshop. Happy to be here. So what I want to talk about is a couple of joint works. So one is finished. This is a work I did there mainly at RVTH. So this is together with Sankar Subramanian Raghunathan. He was a PhD student that I supervised there at RVTH. And then we have another work, which is a joint, it's a collaboration with Mike Giles and Johannes Mayo. So Johannes Mayo is a PhD student at the University of Oslo. This is on reflected diffusions. Okay, so I start with the mean exit time problem. So here is the problem in a nutshell. So you have some kind of bounded open and connected domain, which is a subspace of RD. You have a diffusion process. So this is an Itô SDE. It's an autonomous SDE in the setting we're considering here, but doesn't change much if you make it also time dependent, these coefficients. The goal now is to compute really the expected exit time of the diffusion process, the time it hits the boundary of the domain D. We also do it, we have a finite time horizon. So the exit time is either that the diffusion process has exited before the time capital T, or we view it as the time capital T. So it's one of those two options. And we want an efficient numerical method. And the problem with numerical methods is that there is an instability which is related to how the diffusion process behaves near the bound, whether it exits or nearly exits. Then it can be quite a large difference between the exact process, or the true solution, and the numerical solution. So in order to improve convergence rates, compared to if you have a numerical method that uses uniform time steps, you need to introduce some adaptivity, for instance. So what you can do is to use smaller time steps when you're close to the boundary than when you're far away from the boundary, for instance. But the additional idea that we use is that we also increase the order of the numerical method that we use. So we use a higher order method in combination with higher with adaptive time stepping. And that combination seems to be necessary, but I will make some remarks about that later. It's not completely clear, but at least it works. Right. I will not say much about the regularity, but let me just mention it right away. So we assume now that our boundary is C4 continuous, and we have this kind of C3 regularity constraints on our coefficients. We also have a uniform ellipticity constraint associated to the diffusion coefficient, so this lower bound here. I will not say much about it, but the way it is used is that I can associate this kind of exit time problem to a Feynman Kac PDE. And in that PDE, you get more regularity if you have this kind of uniform ellipticity. And we actually need that regularity to obtain convergence rates. So I'm not going to explain this in detail in the talk. So for well-posedness of the exact problem, you need a lot less regularity. So all the things I mentioned here is just to get the correct rates with my numerical method. So it's not for well-posed. Yeah.
So this upper bound in the ellipticity here, this is basically implying B has to be bounded, right?
Yes, but it is a bounded domain, so it really follows from the constraints on top. So yeah, it's real math. Right, so some applications. So one application is maybe in molecular dynamics. If you have this kind of different molecular configurations and you're jumping from one to the other, and this is modeled through a Langevin dynamics, an overdamped Langevin dynamics. This kind of transition, or these states are pseudo-stable, so transitions happens very rarely. And you want to understand in expectation how long time it takes between every transition. Then you have your molecular dynamics. It's in this well for a long time, but because of this additive noise, occasionally you have a transition over in the other well. So you're crossing the you're crossing the domain boundary, which in this case is just x equal to 0. So if I simulate this SD, it's going to oscillate in a way which looks something like what I have here. And from time to time, you see that I have a transition between the different pseudo-stable wells. So this is the relation. And how often you have this transition in expectation, this is the expected exit time. So the expected time it takes to hit the time 0 from wherever you start in one of these. Another application is pricing of American put options, where you can see that the optimal policy is related to how you hit a boundary surface. So here is a reference interested in. Okay, so this is a problem which has been studied extensively. So there are many methods. So one approach is just the PDE approach. You can associate this expectation of exit time to a Feynman Kac PDE. The drawback with that approach is that if you're in a high-dimensional state space, so your SDE has a high dimension, then you have this curse of dimensionality if you want to solve this PDE numerically, for instance. So it's not very efficient in high dimensions. Another approach is walk on spheres. And this basically, the idea is basically that you freeze your coefficients, then you can compute the probability of hitting a surface. So say that you have an epsilon ball around your current state, and then you just sample a point exactly on the surface with your frozen coefficients. Because when you freeze your coefficients, if I go back here, this is Gaussian distributed, so you can actually compute the exact distribution of your hitting surface if you want. And then you iterate this until you hit the boundary. So you walk on spheres until you walk on ellipsoids, because the shape of the diffusion coefficient is what determines the shape of the set you should sample. You iterate this until you hit the boundary. But when you hit the boundary, you have some complication because it's not very easy to exactly hit the boundary. So this is you can say a drawback with the walk on spheres. But it works well in many settings, and there is a lot of activity on this method right now. Our approach is this Monte Carlo method. So what is nice with the Monte Carlo method is that you don't have the curse of dimensionality, which I'm sure you all. Right, so what is our approach? We numerically simulate our diffusion process. So we are actually going to use the Milstein scheme, or we're going to use the Itô Taylor 1.5 order scheme. I have only written the Milstein scheme here, and I'm only writing it in the setting where you don't have any kind of off-diagonal levy areas that you need to simulate on top of what I write here. So in this case, one time step costs order 1 to simulate. And this is one time step, which is illustrated there. For later, I'm also just going to note that I'm going to continuously extend my solution so it's piecewise constant. Our approximation now is going to be that the numerical exit time is just the first time that the numerical process, which is piecewise continuous, exits the domain. So this is what I'm going to call nu. Okay, so what is known for this setup if you use a uniform time step in your numerical scheme? So first of all, the weak error can be shown to be order h if you're a bit smart. So if you're completely naive and just follow the approach that I've given here, then your weak convergence rate is actually going to be order 1/2. Because it turns out that the numerical exit time is somehow typically much larger than the true exit time. It misses the true exit, so it's a delay of the true exit. So what has been discovered by Brody and Glasterman and later Gobet for more general domains is that if you shrink your domain appropriately, so you shrink it with some order associated to the time step that you use, you should shrink it roughly square root of h in all directions, then you actually improve the weak convergence rate to order h. So you compute the exit time of the numerical problem on a smaller domain than what you should do for the true problem. Right. When it comes to the strong error, uniform time step, it's order 1/2. So this means that if you employ a multi-level Monte Carlo method, you are not going to be in the optimal regime, which would be that the mean square error decays like work to the -1, but you have some additional log terms, multi-level Monte Carlo. Actually, you need some additional tricks in order to achieve this. But our adaptive method can actually remove this log term. So this is the improvement in one sense. I should note anyway that the multi-level Monte Carlo method is a substantial improvement of sort of the classic Monte Carlo method in this setting, because you have a low, strong convergence rate and not too high, weak convergence rate either. Right, so let me just return to this issue of why the numerical method can perform poorly for this problem. So here is this black line here. This is the true diffusion process, and you see that it exits at some time tau here. The boundary of the domain are these blue lines there, whereas the numerical process is slow in picking up that exit. So it's a delayed exit. So nu is, as I said before, you are in this typical situation where the numerical exit time is much larger than the true exit time. And so what we want to handle is how to pathwise reduce this overestimation. I think that's the key. Actually, we want to make the strong convergence rate better, is really what we do. So here is our adaptive idea. So we're simulating our Milstein scheme or some higher order scheme with adaptive time stepping. So when we're far away from the boundary, we're using a time step order h. So when we're delta away from the boundary. But when we're less than delta away from the boundary, we are using order h squared, or we're using h squared as our time step. And I want to refer to this orange part here as the critical region, where we use a small time step. Okay. I guess you can imagine from this that in order for this method to be efficient, you have to figure out a suitable value for delta. Because if you pick it too large, you're going to use a small time step too frequently, and that's going to give you an expensive method. While if you pick it too small, you're not going to improve the approximation accuracy of the method, right? So you have to find a compromise. So what I'm saying is that we want to improve the strong rate from 1/2 now to order 1. And I don't want to increase the cost over the cost of a uniform time step method. And the uniform time step method, when I have a finite time horizon, would have the cost order h to the -1. So the challenge is now to find a suitable value of the delta to achieve this. Okay, so how should it be chosen? So here is the key idea. You should pick it such that your numerical solutions have almost no probability of exiting directly without entering into the critical region before exiting. So it shouldn't be able to exit from inside the uncritical region and directly the next time step jump outside of the domain. Because if it is the case that any exit goes through, or most exits go through the critical region, then you will use a small time step when you exit. And that means that, well, the error can be controlled more easily. That is what it essentially means. So what this result says is that if I pick my delta associated to h in this way, which is essentially order square root of h, then there are very few paths, numerical paths, which do exit directly from the uncritical region. So this is what I want to do. And I'm just going to prove that, or give you the proof idea in the very simple setting where my diffusion process is just a Wiener process. So the first thing to note is that my numerical scheme is not going to use more than this many time steps. If I always use the find time step, I would use this many time steps. Okay, so now I want to ensure that none of my time steps are longer than the width of the critical region. If I ensure that, then of course I'm excluding this kind of exit property. Right, so this I can bound from above by the total probability of any of these intervals being larger than delta. But that again, for each of these, are of course bounded from above by the maximum over the full interval being larger than this. And now I take even the interval in the case that this is order h interval, and I sum over, should be capital T over h squared. Okay, and then there is a result now, which is called Bernstein's inequality, which means that I can relate this probability to an exponential of delta squared divided by what I have here. Should be a parenthesis here as well. And when I choose my delta to be square root of h times log 1 over h, I get precisely what I wanted to achieve here. So this tells you, I mean, if you go backwards, you see exactly why I should have these results. The dimension here doesn't enter when I have a Wiener process, but it does enter when I have a more complicated multiplicative mass of the dimension. Okay, so that is really the essential property that we need to make use of. Because of this, we actually achieve a strong convergence rate, which is essentially order h. So it's order h minus psi for any psi positive. I'm going to write it order h 1 minus. Proof IDs. I'm not going to say so much, but let me split the strong error into two events. So the event that the numerical exit time is smaller than the true, and the opposite event. So for the first setting, I can, with some calculations, I can bound this from above by some Lipschitz constant of the Feynman Kac PDE times the difference between the true path and the numerical path at the numerical exit time. And this again, I can bound just leaning on the order of my numerical scheme. So when I use a Milstein scheme, I get order h. If I use a higher order scheme, I get a better order. So that's the first term here. The second term, what I do is that I'm considering the exit time of another problem. So I'm adding an additional boundary to my domain D. So I'm using the Minkowski sum here. So I'm padding a ball. So this is just a set sum. Padding a ball of radius r to my domain. So I make a slightly larger domain. And then I'm asking about the exit time, the true exit time on that larger domain. That true exit time is, of course, later than the exit time on the smaller domain, because my domain is now large. So that's the case. But it turns out that if I choose to scale my padding correctly, the probability that my numerical exit time on the true domain is larger than the new exit time is negligible. So it's order h. So I just have to figure out how large I need to enlarge my domain in order to control this. So my term 2 here is tau minus nu. So that's clearly, and nu is larger than tau. So that's clearly smaller or equal to tau r minus it's clearly larger than tau r minus tau, because with very high probability tau r is larger than u. So I just have to use a triangular inequality to take into account the other setting where this doesn't happen. Okay. So altogether I get a similar kind of convergence rate here. The point is that the adaptive time stepping, the error control enters in this probability estimate here that my numerical exit time is larger than tau r. So all I want to say here, this is not really a fair representation of the proof, but what I want to say is that here you see how the order of the scheme and adaptive time stepping enters in our error estimates. So how we need both of these properties. But I should be more careful because we don't have a lower bound. So perhaps it is possible to get away with this without enforcing both. It does, however, seem from numerical estimates that it's not likely. You probably do need both. So that to say. When it comes to the computational cost, we define it as follows. So the cost is just the number of time steps my numerical scheme needs until it exits, because then my computation is, of course, finished. And the delta t of x is now the time step at point x, because I have defined it this way before. So it's either h or h squared. And I said before also that each iteration of the numerical solver is something that we assume costs order 1. So if you use the Milstein scheme or some higher order scheme, and we have this kind of off-diagonal Levy areas that we need to compute, then that is outside of the assumptions that we make here. You have to add the computational cost of that as well to our computations. But under these assumptions, we obtain this result that the expected cost of our numerical method is almost the same as the uniform time step method. So it's order h to the -1 plus some extra log term. That's all we do. So here is a rough idea how we control it. So again, we enlarge our domain. So now we pad it with some ball which has a size delta. Same delta as in the adaptive time step. Then our cost is defined as this. Now, there is a small or equal to some cost associated to using just the largest time step everywhere, and then a cost associated to using the smallest time step when you're in the critical region. So this is what I have inside here, is the occupation time inside the critical region of my numerical scheme. Now, it turns out, because of the higher order scheme that I use, that I can bound the occupation time of my numerical scheme inside this region by the occupation time of the true scheme inside a larger region. So it's inside like a larger domain, but also a larger region. So this we can show is true. And this occupation time I can also compute. So I can compute the Fokker-Planck density for this diffusion process. And this is a Fokker-Planck density because it is an exit time problem that has 0 boundary conditions. So Dirichlet 0 boundary conditions. So that's why the order of this occupation time is going to be order delta squared. Delta was chosen as square root of h times log h. So in absolute value, so that's why you get the cost.
And one is using this bound on the diffusion too, right? To get that. Not.
I think I mean, you are using the uniform ellipticity at least to ensure that it is you have the sufficient regularity in the that's true. Okay. So I also have a motivation here for the Wiener process, but let me go on. I don't. So okay. So here is one numerical example just to illustrate the efficiency of my numerical method. So it is a problem where you have some mixing. So you see that you have some mixing in the drift coefficient here. It's a 2-dimensional problem. You have your domain is just a ball, and we want to verify the rates. And let me just quickly show you the boring plots. So here we have the correct rates. So it's either order 1.5 or order 1 for the numerical methods. And we have the right computational cost. So I will just quickly skip this. Sankar also did some extensions which are not in the paper that I'm going to mention later. So that is, he extended this method to a Monte Carlo method. And I think this second pointer is very interesting because if you are in a setting where you have an SDE that can be simulated exactly, so you don't need to do numerical approximations of the path, so it could be a GBM process or it could be just a linear path, then provided that your domain is C4, you can actually compute the, you can do strong approximations of the true exit time to any order that you want. This is kind of cool. So you just need to add more and more critical regions with smaller and smaller time steps close to the boundary in order to make this work. And the cost is not going to grow. Okay, so let me shortly say something about the second problem. So this is a work in progress. So this is a reflected SDE problem. So here you have your differential equation. It looks like an SDE, but then you have an additional term here that I will describe below. Again, we have some domain D, which is in this case smooth and convex. And the new here, the new function, is a vector field, and on the boundary of D is going to be an inward pointing normal. So it's going to sort of push your process back into the domain, is what is pointing. L here is your pushing force. So let me associate it to a Skorohov problem. So if you're given an adapted CAD-like process, YT, that starts inside of the domain, and you also have smooth coefficients A and B in your, say, SDE on top here, then there actually does exist a unique pair of adapted processes, so an X and a capital L, such that if I correct my given process Y by subtracting this integral, my resulting process X is going to stay all the time inside the closure of D. My process X is going to solve this kind of reflected SDE that I'm presenting up here. And my process L is actually going to be the occupation time on the boundary. So it's going to just count how much time I spend on the boundary. And this process is going to be almost surely have bounded total variation. So this is the result. So this is the numerical method that we consider. It's a splitting method in some sense. First, we solve the SDE part. And the second step is to approximate the L integral that I'm considering here. So it's approximated by projecting the numerical solution back into your domain if it has exited the domain. So here's an example. If I have just the hyperplane or the half space in R2 with Y, the second component being positive, then my projection back in is that I take the maximum of X and X2 and minus X2. This is how it looks. So again, we want to construct an efficient numerical method for approximating the diffusion, the reflected diffusion process in this case. What we do now is, again, to use a smaller time step when we're close to the boundary of our domain. But we have to be a bit more careful in this setting than in the mean exit time setting. So what we have is like a smooth transition from the coarsest time step to the smallest time step. So it transitions between time steps depending on how far you are from the boundary. So you could maybe think of this as the supercritical region, and here a somewhat critical region begins. So, and when you're farther away from the boundary, you use for range. The challenges is that actually what is known theoretically is that you have very slow strong convergence rates for the uniform time step projection method. So if you have just a smooth convex domain, your mean square strong convergence rate is order 1/2. A second problem here is that the occupation time near the boundary is much larger for the reflected problem than for the exit time problem. Because for the exit time problem, you exit very quickly when you're close to the boundary. And that means that it's much more challenging to construct an efficient adaptive method. Okay, so now my time is up. So all I want to say is now the cost becomes much larger. The approximation error depends a lot on the shape of your domain. And these are the results we have achieved up until now. So we only know that for some domains, we are going to get an improvement in the efficiency at this point. But we are working on this to see whether we can figure out something better. I should also mention that for some domains, we actually need to use the Milstein scheme here in order to achieve the correct rate. So, okay, sorry for babbling on, and thank you for listening.